Hello and welcome to part 3 of video 1 about feature engineering, dimensionality reduction, feature selection, and feature extraction. In part 2 of video 1, we basically theoretically discussed different methods of feature selection. Primarily, we discussed filter methods theoretically, we discussed wrapper methods, and we discussed embedded methods. In this video, we are basically going to do the hands-on Python examples of all these methods, just a very few and simple examples on a real data that is basically accent recognition data. I have downloaded that data from machine learning repository, UCI machine learning repository. That data is uploaded very recently in 2020. So let's go to Python and practice filter methods, wrapper methods, and embedded methods. So for that, I go to Python. I import some of the libraries needed. Import pandas, for example, as PD. Import numpy as np, mostly always required. Import, for example, sklearn, that's the library scikit-learn, dot feature selection from basically I need to import something from here. From this import basically select k best. So these are the imports that we really need. Select k best is basically a filter method that selects the best k features out of the available features. So let's say we have that. What's the problem here? NumPy ufunc size change may indicate binary incompatibility accessed like so. Yeah, that might be an issue. No, that's not an issue. Okay, so then we import some data. Let's say where is the data located? Let me just go to that file, the accent recognition data. Let me open up that file and show you that data in Excel. That is basically there are 12 attributes, and one that's a classification data with language attribute as a class label, and rest of the data. This data is basically uploaded in 2020 on UCI machine learning repository. Very recent data. We are going to work on this data. So let me copy the path for this file. So that is this. Control C, and then we dive in again to this. So df is basically pandas pd.read csv, and then we have this r, and then inside that we have this data. So data is read. Let's just see what the data looks like. So df.head. So this is the data with this language attribute, and there are several other attributes as well. Basically the 12 attributes. Yeah. So let's apply this filter method that is encoded here in select k best on this data, and let's select, for example, let's select top 5 attributes based on certain criteria. So let's do that. First of all, let me separate out the target value, which is df.language. That's the target, and let me separate that out using np.asArray rather than data frame. Let me pick that as numpy array. So x is, which is all the rest of the attributes, is df.drop language x is equals 1, and then I want to pick that also, again, not as a data frame. I want to pick that as numpy array, as array. So let's see if everything is fine there. So I guess yes. If you see x.shape, that is there are 329 records with 12 attributes. If you see y.shape, that is basically 329 total basically labels. If we see np.unique, for example, y, then that is, there are 6 classes and there are 6 labels are there. Okay. So now what we do is we basically select certain models. So let's say we have filter method f, which is select k-best, and let's say we want to select the top 5 based on certain built-in criteria. Here the built-in criteria is f classify for classification, and for regression there are other criteria that we will be seeing shortly when we will be seeing the documentation of select k-best. So then we have our transform, let's say t, which is the selector, which is f.fit xy, that's the selector. And then what we do is we say okay, t dot scores. So let's see. So here the scores for feature number 1 is, this is the score, whatever the score criteria was, that's the score for the second one, that's the score for the third one, and so on. You can see, I mean, this is the highest score, which is 20 point something. That is the highest score. Then this is the then this is the second highest. Then I guess this is the third highest, and so on. We want to pick 5 best. So let's generate x new. X new is t dot transform x, and here we'll be having x new dot shape, that will be containing the top 5 features. Just selected the top 5 features. You might be thinking how this selection happens, what is the criteria inside. So let's see the documentation of this select k-best. One way to see the documentation is just write question mark shift enter, and the documentation will open up in front of you in Jupyter as it is. So there are several ways of so one is the criteria, score function or criteria that you have to set. Here we didn't set any criteria, so the criteria by default is f classif. There are other criteria as well. Then you have to set the number of features that you really want to select. To see a lot of criteria, and then there are certain attributes that are returned, for example different scores and the p-values. There are examples as well. If you want to see all different kind of criteria, you have f classif, that is analysis of variance, and of f value, that is by default for classification task. You can set this criteria, mutual information classif, mutual information for discrete target. If the target is discrete, you have chi-squared criteria, but that requires your feature values, all the feature values must be non-negative, and the task is classification. And you can have mutual information for regression if your task is regression, and then there are several other related functions for feature selection. Yeah, so you can see in there, and you can just work for that. Next we talk about, so that was the filter method, just a very brief filter method using select k-best. Next we talk about for example we talk about we talk about the recursive feature elimination. So how can we apply a wrapper method by using recursive feature elimination in Python? How can we implement that? So for that we have to import certain things from sklearn, for example, dot feature selection. From sklearn feature selection, we have to import a model for recursive feature elimination. We also have to, we need also to have some classifier. For example, we may come up with a model, let's say linear SVM or something like so. So we may import some classifier like from sklearn dot SVM import. We have several options here. We can import linear SVM, for example, linear SVC, linear support vector classifier, for example. Let's import that. And now our model base. So these are the imports we really need. We need to import some wrapper, some model, we can change that model. Whatever model we need to import. If the task is classification, which is right now the task is classification, we imported a classifier SVM, linear SVM. If the class is regression, you might be importing some regression model here, and then we have to import the recursive feature elimination method, which is the greedy approach to build a subset, as we have seen earlier. So next we initialize our model, whatever the model or the black box we actually is working with. So let's say model is linear SVC, that's our model. Perfect, that is defined. And next we define the recursive feature elimination selector. Let's say S is RFE. Let's say that is our, where we give the model and the total and the top features we really want based, and the total size of the subset. Here the size of the subset we are defining is 5. Let's say we want to get the 5 features, the best features that is there with this linear SVM. So that is there. Now what we do is we actually fit the transform, and we get basically let's say S2, or let's say the transform T as S dot fit, like earlier, X and Y. X and Y, again we have our data, which is the accent data. We have already finalized these X and Y's there. There is a warning, number of iterations, convergence. Okay, fine. These are certain warnings. We can suppress those. So after this transformation is done, we have this T available with us, which is this T. This T is available with us. Now we can see the support of. We can check the support of different. So we can check the the support of different features. What features basically are selected. So T dot get support. If you just print that out, you will see, for example, certain features are being selected, and the others they actually are not selected. So let's say, for example, rather than writing this get support, let me write that as, let me just get the mask out of it. T.get support, that will give me a Boolean mask, and if I just print that mask, I will get to know which features are selected. So feature 1 is selected, feature 2 is not selected, feature 3 is not selected, feature 4 is not selected, 5, 6 is not selected, then this feature is selected, then this feature is selected, and we have these 5 features that are being selected. We can for example, we can find out the names of these features. What are these features that are basically selected? But that's what this basically is. Ideally, what we should do is we should basically split our data in a train and test, train and validation splits, and we should apply this cross-validation kind of for validation stuff. But there is a built-in support for cross-validation as well. If you just import RFECV cross-validation, that will actually do the whole stuff for you without actually extra line of coding. So you'll be having this RFECV, and rest of the story will be same here. You have to give, for example, RSVCV, and here you have model. You have to give the cross-validation support, how many cross-validations you really want, and the rest of the story is almost the same. So this, here you have this, which is doing certain cross-validations. This static is there because of the cross-validations, and then after this, all this cross-validation, you have this mask, and you have now certain features that are being selected. One benefit of this cross-validated recursive feature elimination is you need not to specify the total number of features that you really want to pick. it actually picks the best features, the total number of best features automatically. This number here, CV equals 5, actually refers to the total number of cross validations. The how many of, so for example, 2-fold cross validation means you have to split data in 2 directories. 5-fold cross validation means you have to split the data into 5 partitions, and you have to apply this stuff. So that's the wrapper method, just very briefly, using linear SVC. By the way, if you change this model from linear SVC to some other model, for example, if you want a logistic regression or something else, the rest of the story will stay the same. And with respect to that model, you might be selecting this feature. So one way to select the generic kind of features that are model free, you select features using a lot of different models, and then pick the majority vote of the features and select those. So next we basically talk about the embedded method using this linear SVC again. So to use embedded method with, let's say, L1 norm. So for that we have to do certain imports. So we already have imported linear SVC. So let's say we are using linear SVM with certain parameters inside regularization parameters, and then we will see what kind of features we have really selected. So embedded methods, for that in Python we have to import the select from model, sklearn dot feature selection, import, for example, select from model. So that is for embedded features. So we have this import. We already have our data X and Y available with us. So let's build a model. For example, M is linear SVC, and you can set certain parameters. For example, that's a regularization parameter. You can set a penalty term, which is what kind of regularization you really want, whether it is a L1 regularization, L2, or what. In this case we are setting L1, and we are not going to dual. There is a concept of dual criterion in support vector machines, so we are not going to do that. So that's our model. Next we fit that. We fit our data into that model. So oh, what's the problem here? Got an unexpected keyword, penalty. I guess I have wrong spelling of this PN. Oh, this I is not there. Yeah, this I is not there. Penalty. So yeah, it works. Now once we have this model, we can have this transform or select as select from model. Select from model, and we select from model basically by applying this model, and there's a parameter prefit that we can set as true, and this is basically the transformation that is done using the embedded method for linear SVM with these kind of penalty terms. We could have done the same thing with tree-based classifiers as well, or the other classifiers, or basically any regression model using ridge regression or something else. Almost all regularization models, they fall under the embedded methods. Now we can select our xnew, which is simply t.transform x, and after that we can check the shape of this xnew, which is it is 329 to 329. Why haven't it why it did not actually reduces the it should have reduced the in this particular embedded model, it looks like that all the features, they are important. I mean, all of them. Let's load another data and check for that. Let's load, for example, iris data. Why not? So let's say from sklearn dot datasets import load iris. Let's import that, and after that we might have our x, y as load iris, return x, y true, and this may return us x and y, and then we just repeat everything that we did so far. Here x dot shape is 4. We have 4 features, and let's say we have our model as linear SVC with C value as 0. Let's say 0.01, and penalty as L1, let's say, and the dual is, let's say, false. We want to fit that, fit XY. That's our model M. And liblinear failed to converge, fine. Then we have our transform as select from model. We have our model M, and then we have prefit equals true, and then basically we have our x new equals t dot transform x, and then we have to show that x new dot shape is what? In this particular case, we actually have 3 features. Previously we were having 4 features. So this is just the data set. I mean, the data set that is this accent recognition data set with linear SVC embedded model with these kind of parameters. All the features, they become important, and the feature reduction never happened. But in the case of iris data set, for example, this linear SVC with these kind of parameters, it actually just picks 3 important features, but the care must be taken, because these 3 features, they will work very well in the settings that you have done so far. So don't actually use these selected 3 features with some other model other than linear SVM. Yeah, so that's what the embedded method really is. So yeah, so this is a very small kind of workflow of filter methods, wrapper methods, and embedded methods. To see much more detail about these, and to see how to implement these from scratch, these kind of models from scratch, and to understand much more theory on real data sets, I will recommend to you to basically go to our official course on AI sciences and enroll that course on this feature engineering. We have a full-fledged course on that, where we discussed all these things in much more detail, and all these kind of Python implementation, a large variety of those from scratch and several of those from the built-in methods. So that will give you much more grip on these kind of methods. So that's about video 1, part 3. In video 2, in the next series, we will be discussing the feature extraction methods, primarily the principal component analysis in that. So hope you have liked our content. If you really liked our content, please press the notification button, like it, and share it among the rest, among your friends, so that several people gain the information that is here in this video. So yeah, hope to see you next time.